Okay,
Okay.
it's a great pleasure to introduce Agnes, and she's already willing to speak. Please go ahead.
Okay, thanks a lot for Alicia, and thanks for the organizers to invite me to give this talk. So this is an ongoing research, it's still in progress, joined with Teresa Crick and Bernard Morin about univariate rational sum of squares. So I will start with just a few words about the motivations. So the fundamental problem that I will call the global non-negativity problem is to decide whether a polynomial is non-negative on the real n-dimensional space. And this is a computationally hard problem. And to make it more feasible, people consider a relaxation, which is to decide whether this polynomial is a sum of squares of rational or of real polynomials. And it's well known that this is a relaxation. It's not an if and only if the Motzkin polynomial is a counterexample. On the other hand, Parillo in 2003 wrote a short paper about what I call the local case, where he is looking for an idea that, looking at an idea that's a radical zero-dimensional idea, and he proves that a polynomial is non-negative on the finite real set of common roots of these polynomials, if and only if there is a G is a sum of squares modulo these ideas. And so this was our starting point. And in this talk, I will talk about the existence of a rational, what I call a rational certificate of non-negativity. And by which I assume that the input polynomials all have rational coefficients. And we also assume that G is non-negative on the common roots of the idea, the real roots of the idea. And the question is whether G is a positive combination of rational polynomial squares modulo the idea. So this is the expression I'm talking about. So here we allow these weight numbers that are also rational, and this really just allows to, it's not essential. You can get rid of them in the, by adding more sums, but it's just much simpler to write it this way. And that was the motivation, and we started this work looking at the simplest possible case, the univariate case. So in this case, we are only given two polynomials, f and g, and you assume that g is non-negative over on the real roots of f, and the question is whether g can be written as a rational sum of squares modulo the polynomial f. So that's the problem I'm going to talk about, the univariate case. So people haven't really looked at much this question in the local case, but they did look a lot in the global case over Rn. So a simple exercise shows that if G is non-negative in the univariate case, then it's a sum of two squares and of real polynomials. And Landau already in 1905 proved that it's also a sum of 8 squares of rational polynomials. And this was improved to 5 by Porchet. And in the multivariate case, Strumfels asked in 2007 that if G is a sum of squares over the real, whether it is also a sum of squares over the rational polynomials. And Pei and Parillo has a paper in 2008, I will talk about it a little more later, that proves that if G has what I will describe as strictly feasible sum of square decomposition, then over the reals, then it also has a rational sum of square decomposition. However, in general, the answer is no. Shader in 2013 gave counterexamples for every number of variable greater or equal than 2. Now, turning to our case that we studied, the local univariate case, I just stated here Parillo's 2003 result for the univariate case. So in this case, you have f and g, and you have to assume that f is square free. And then he proved that g is non-negative on the real roots of f if and only if g is a sum of real squares modulo f. So what we will consider is the following. The first question is I call the existential question over the rationals. So with the similar assumption, we will consider the case when f might not be square free. So we will try to get rid of the square free assumption. And g is still non-negative on the real roots of f. We are trying to find the rational sum of squares certificate modulo f. And both Parillo's construction and our existential construction, you will see it uses the roots of f. So from an algorithmic point of view, you don't really want to compute the roots of f. If you have the roots of f, you can actually already certify the positivity or non-negativity of g. So when I talk about an algorithm that computes such a rational sum of squares, I will talk about something that doesn't need the roots of f. And finally, it's still an ongoing research to try to give bounds on the bit size of the numbers in this rational sum of squares. So let's jump right to the main existential result, what we could prove. So in the univariate case, given f and g with rational coefficient, and f may not be square free, and assume that g is non-negative of the real roots. And we need this extra technical condition that is much weaker condition than f being square free. So what it says that if the GCD of f and g is non-trivial, we allow that, but we still require that this GCD is relatively prime to f divided by the GCD. And I will give us a very simple example in the bottom here that shows the necessity of this condition. And then with these weaker conditions, we were able to prove that G has a rational sum of square decomposition modulo f. So this is what's written here. So this little example that I have here is an example when the GCD of f and g is non-zero. So f is x squared and g is x. So the GCD is x, but f divided by this GCD is not relatively prime to the GCD. And in this case, it's easy to see that x can never be written as a sum of squares modulo x squared, because in the right hand side here, you can see that there cannot be a linear term with non-zero coefficient, right? So this equation can never be set. So this for the rest of the talk, I will mostly talk about the main ideas how to prove this main existential result that we have. So the starting point was, as I said, Parillo's 2003 construction, and here I will explain it in a very simple example with a polynomial x to the third minus 2 with 3 roots, 1 real and 2 conjugate pairs, a single conjugate pair. And I chose G to be X to be simple, but it really doesn't matter. In this slide, I never use what G is. And the main ingredients of these constructions are the Lagrange bases corresponding to these three roots. And these are univariate polynomials of degree at most 2 that give 0 on one of these three roots, depending on the indices. So the construction of Parillo is the following. It gives G as a sum of squares. So the first term, this corresponds to the real root. And if you have more than one, you have for each real root 1 squared like that. So this is G evaluated that root, which we assume to be a 0 or positive number, non-negative number, multiplied by the square of the Lagrange, corresponding Lagrange polynomial. And then in the construction for each conjugate pairs, we have here one conjugate pair, you have a single square. And you can see that because these roots were conjugates, this is a sum of two polynomials that are conjugate of each other. So the imaginary part cancels. So we actually have a real polynomial in the square. And to prove that this gives G modulo the polynomial f, you simply have to substitute the roots in both sides and get equality. And you do get equality because when you substitute the roots in the Lagrange basis elements, you get zeros and ones, so their square is still 0 and 1. And so we will use this one more time in this talk, this idempotency of the Lagrange basis modulo the polynomials. Okay, so we heavily use in this proof that f is square free. Yeah, so it's not trivial to get rid of it, but we did manage in a different way. Okay, so before I go further in this construction, let me quickly show you how to do the exact same construction using matrices, because we will use this notation from now on. And many of you probably seen how to write sum of squares in matrix format. So in Parillo's construction, you consider the van der Monde matrix corresponding to the three roots. I again described this on this simple example. And then the inverse of this van der Monde matrix has the property that its rows give the Lagrange basis element, easy to see. Now the core of Parillo's construction is this delta matrix. It's a block diagonal matrix. It has a 1 times 1 block for each real root, and it has a 2 times 2 block for the conjugate pairs. And so on the diagonal, it has just simply the evaluation of G in the conjugate pairs, but the off-diagonal entries are also filled here with the lengths of that evaluation, which is the same for the conjugate pairs. And then finally, the Q matrix is constructed using both the U and the delta matrices. And here I just give you, just to see for this particular example, the numerical matrix, so that you see that this is a real matrix. Parillo proves that this is always a real matrix. But in this example, it's a non-rational matrix. And then again, to prove the correctness, you take this matrix Q and you multiply from the left and the right with this vector of the powers of X. And then using the properties of the U matrix, you get that for this block, you get this term, and for this 2 times 2 block, you get this term. And the second term you immediately see is a square, the same square that we saw above. And the proof of correctness is the same as before. And just want to notice that Q is again a real matrix. It is a positive semi-definite matrix, but it's rank deficient. Okay, so now that we set this notion of this, how we, this matrix and the polynomial correspond here, I will give the main ideas of the paper of Per and Parillo from 2008 that construct an approximate rationalization of a real solution. So to start with, I define this linear space of the pairs of matrices and polynomials that satisfy this constraint. So it gives G mod F basically, and it is a linear constraint on the entries of the matrix and the coefficients of the polynomials. And within this linear space, we would like to find a positive semi-definite, an instance with a positive definite, semi-definite capital Q. So the outline of the algorithm is the following. Assume that you have an approximate for an exact solution, and you have to assume that this is a strictly positive definite solution. So this is what I mentioned as a strictly feasible solution. So we have some positive distance of this matrix from the singular matrices. And then in the next step, you find some rational approximate of this exact solution, or its approximate, such that you have half the distance from the singular matrices. So this rational matrix is also going to be positive definite, but it might not lie in your space where you would like to have. So the third step is simply projecting this rational matrix to the, or this rational solution to the linear space, and then you get an exact rational solution, and it will also have a positive definite matrix in it. Unfortunately, as I mentioned already, Parillo's construction is not, sorry, this is wrong, Parillo, 1L, 2 Rs. Parillo's construction is not strictly positive definite. This matrix is rank deficient. So to prove our case or our existential result in the generic case, so in the case where F is still square free and the GCD of F and G is 1, we notice that actually Parillo's construction is minimal in the sense that in this 2x2 submatrix, he put the minimal possible value that still works, but if you increase it, you will still get a perfectly working solution, but it will be strictly positive definite, and it will be full rank. And so as a consequence, we can apply for this exact solution the rationalization, the approximate rationalization that I described, and you get the rational, exact rational solution for the problem. So this solves the generic case. So next I will give the main idea. Oh no, next I just have the same toy example, how it would work. And really I just want to go through very quickly of this slide. So here I use twice in the off-diagonal entries of this matrix, I use twice the length of the G of at the root. And this is the exact solution that you would never compute. And then because the smallest singular value of this matrix is fairly big, so the distance from the singular matrices is fairly big, a 1 decimal rational approximation of the exact result will work, and after projection, we get an exact rational solution with fairly small entries. And then here, this is my slide about the algorithm without. There are many versions, or not many. We were thinking of 2 and comparing 2 versions. Here, I just give the simplest one. You can phrase this problem as a semi-definite feasibility problem. easily. So if you solve that, you will get a strictly positive definite solution or its approximation. And then you do the same thing here. Again, we have a big, fairly big distance from the singular value. So again, 1 decimal approximation and then projection gives this small solution that's a tiny bit different than the previous one, but similar. Okay, so now let me start talking about the non-generic case. So the first thing is how to handle when f is not square free. And we may assume that the GCD of f and g is 1. So I will present, sorry, first we prove a Hensel lemma. So it's a straightforward Hensel lemma, but it actually produces sum of squares. So if you have a rational sum of square decomposition modulo some polynomial q, let's assume it's an irreducible polynomial over the rationals, then for any exponent, you can lift it to another rational sum of squares modulo q to that exponent. And to prove this, the main idea actually is to reduce the case to the case when G is a single square. So it's not a sum of squares, just the square itself. And then use the Newton iteration for the square root function to get the result. So that's the main idea here to prove this Hensel lemma. And then the next ingredient is to glue together these irreducible powers, is to use Chinese remainder. And again, we had to modify it a little bit. So the conditions are similar. You have relatively prime polynomials, and for each of them you have given as a rational sum of square decomposition modulo that polynomial. Then you can glue them together to get a single sum of square decomposition of G modulo the product of these relatively prime polynomials. And here the main idea is exactly the same as in Parillot's construction, namely that there the Lagrange interpolant, we use their idempotency, and the Chinese remainder theorem is basically just a Lagrange interpolation. So it works, or a generalization of it. So it works in a very similar way. And then, so these two, the Hensel lifting and the Chinese remainder theorem, allows us to handle the non-square free case. And then finally, to handle when the GCD of f and g is not trivial, but we still have this extra condition that this GCD is relatively prime to f divided by the GCD. Again, algorithmically is not very hard to handle. We had to do little tricks because again, you have to end up having a sum of squares. So basically the main idea is that to first consider so D is the GCD of f and g, and we will have to divide by it modulo f or modulo f over D in the end, because you will see why. So, and then instead of trying to find the sum of square decomposition of G modulo f divided by B, we will have to find T times G, this inverse will come in. And then here I chose this example. Sorry, I didn't tell you what's this example. So here this example is, I changed the previous one to be x and then the square of the previous polynomial in the toy example. And then G is x, so that GCD is still x. So here we still have a square. So you see here that first you write G as a sum of square modulo this polynomial without the square, the same as previously. And then the next step is hand cell lifting. And you can see that in the hand cell lifting, we only lifted one of the squares, not the other two. So we only lifted this square and we got this ugly thing here. But from the existential point of view, we lifted it there. And then the last step, why we needed this inverse, is to multiply both sides by d square, and that will be absorbed in the squares here and canceled by the inverse here. And then it will give us the modular relation modulo the input polynomial f. So again, it's just really do not need a lot, but a little tricky. So let me conclude it. I'm over time. So we proved the existence of a rational sum of square certificate with this extra condition. And we also gave a symbolic numeric algorithm. It's a numerical algorithm using semi-definite programming and rounding in the generic case, and Chinese remainder hand cell lifting and extended Euclidean algorithm in the non-generic case. And finally, we are working on giving bounds. We already handled the general case for the size bounds, and then we still haven't dealt with the non-generic case. So it's a work in progress. Thank you very much.
Thank you, Agnes. I'll clap with sound. So, are there any questions for her?
Hello, you hear me?
Yeah.
Okay,
Yeah.
so hello, Agnes. Very nice talk. Just yes, this question about this thing about Parillo. So in his work, when you have a positive definite matrix, then you can round and get a rational solution. But in some cases, there is no positive definite matrix.
Exactly.
So what you're saying, you prove is that in your case, it's all you can always find this positive definite matrix. Or
no. I think no, it's not. No, what we prove here is that with these symbolic tools, you can reduce the case when there is no positive definite matrix to the case where there is positive definite matrix.
Okay, in this case, you modify your matrix. So you're proving that you can always get a positive definite matrix.
Yeah, by some symbolic modification. Okay. So basically by dividing out from, so for example, if G and F has common root, then this algorithm here is more or less dividing out that common factor, and then G will be strictly positive on the remaining roots, and that's what we use. And for that, we can apply the Parillo, something of this sort.
Okay, yes, thank you.
Mm-hmm. Okay, thank you very much, Agnes. And we now move to